So in general, properties of transition metals. The transition metals seem very similar to each other when you compare them to the differences in the main group. I mean, in the main group, we've got nonmetals and metals, and we've got gases and solids, and all the transition metals are metals and they are solids. So they're kind of the same. And they have moderate to high densities, they're good conductors, high melting points, moderate to extreme hardness. They also have similar electron configurations in that all of them have electrons in the d orbitals. So as a whole, they're very similar, and yet they do have their own unique properties. Come on. There we go. Is that it? No, there we go. So if we move across a row of transition elements in the periodic table, and if this is giving you flashbacks to Chem 1A, it should, because we're using that again, right? Electron configurations. So here we have scandium, the 4s sublevel fills, and then we get one electron in the 3d. And then adding another electron, these begin to fill up the d orbitals. Chromium is weird because instead of, well, the new one goes here, and then this guy came from over here. One of the 4s electrons goes over there. And so, that's like a Groupon deal, or, it's like this special buy one, get one or something. You save money if you've got all your sublevels exactly half full, right? So even though this orbital is a little higher in energy than that one, there's a payback that's big enough. Yes?
Is that probably why chromium has so many different oxidation states?
I honestly don't know. Manganese has a lot too. I think it's just because they have so many electrons there. They have more they can lose. So here, manganese keeps this half-full one and fills this one up, because completely full or exactly half full are more stable. And so then we've got iron, cobalt, nickel, they're following the pattern, and then copper is strange, because here, by moving the 4s electron up here, we can have this half full and this full. And again, that's a bonus. And then here we have zinc that has all of these full. Now, what I tell my students in Chem 1A is that the chromium and copper weirdness is the only one I think you should try to remember. There are other transition elements that do strange things as well, but I don't see any point in trying to memorize those. Yeah, this looks like some bad math equation, doesn't it? In the first two rows, we've got noble gas, and then we're filling the NS. So on the periodic table, so if you've got potassium and calcium, and then you're filling the D sublevel that's one less. So instead of 4s, it's 3D. And then you get into the F rows as well, and that's N-2, and then N-1 for the D. And then there's a lot of exceptions. Half-filled or completely filled orbitals are more stable. And this is important. Transition metals lose electrons from the NS orbital before the N-1D. So these guys, when they lose the first electron, it'll be a 4s electron. It is not reverse order of filling, okay? But this is the highest occupied principal energy level, and therefore those are the valence electrons. In the quantum hotel for electrons analogy, a tornado comes through and takes off the top floors, and so it's only going to get these guys. These guys are in more expensive rooms, but they're a floor below, so they're spared. It's not until these guys are gone that you start taking those away. So once you remove the 4s electrons, then you can get into removing the d electrons. Any questions? Yes.
So just quick clarification. So the valence electrons were in the 4s region?
Mhm.
Okay.
Yeah. So to find the valence electrons, you're always looking for the largest principal quantum number. So if we look at this one, 4 is the largest number that we see. This is 3. And so for all of these guys, you'll see that it's the S. Well, I'm sorry, these guys have P's. But for all of these, it's going to be the S electrons that are the valence electrons. So we should be able to write electron configurations for transition metals. Write the ground state electron configuration for osmium. So osmium is number 76. I'll just go point to it on here. It's right here, osmium. And so to write the abbreviated electron configuration, we go up one row and all the way to the end to find out what is the previous noble gas.
Xenon.
That's xenon. So then we come over here. This is the 6th period. This S block is the correct number. So this is 6S. And then this is D block, and this space here, it goes right to the F. And this periodic table on the wall is actually how it should be, right? Now, if you want to ask me, well, why anything, I probably don't know. So there's that. So we've got 6s2, and then there's 1 in the D, and then it jumps to the Fs. Why? I don't know. And honestly, don't care. So when I look at this group, the D block, you see how we've got stair steps coming down here? Let's change this to a color that we can actually see. It's coming down the stairs, right? I expect this one to be up here, but it's not. If it was up here, the D would match with the period number. So this group, this block, sunk down 1. And so, this is 5S, and then this is 5 minus 1, 4D. And then this is sinking another time. So we have 6S2. We'll just put that guy on hold for a minute and go down here. This is 6th period minus 2, so 4F, and fills up through 14. And then we pick up in the Ds, 5D, 10, except we don't need to go all the way. We can stop right here. So there's 1, 2, 3, 4, 5, 6 in the D. Actually, I think I'll just write that on here. So we have xenon, 6s2, 4d14, 5d6. Yes. Yeah, just trying to see if you're paying attention. So, any questions about that? This is, taking it a little further than in 1A. Write the ground state electron configuration for niobium 2+. Where'd you go?
41.
41, next to zircon. So number 41. So what is, a good thing to do is to write it for the atom first and then write for the ion. So for the atom, what would be the noble gas that we would start with? Krypton. And then after krypton comes what? Rubidium. So we've got 5s2. And then where yttrium is, Y, what level is that? 4D. And then we go over 1, 2, 3. Right? 4D3. So that's niobium with no charge. So where are we going to lose 2 electrons? We're going to lose them from here because this is the valence shell. The valence electrons are lost first. They are on the outside. So it doesn't matter that these guys came in after, it's the valence ones. And since there's 2 there, we can just get rid of those. Goodbye. And krypton 4D3 represents niobium 2+. Any questions? Real common mistake is to forget to take the s electrons first. And you can pretty much guarantee, well, actually no, because this is the take-home test. But there could be a question on the final where they try to trick you with that one. I was going to say I would trick you with it on the midterm exam, but it's not on there. So let's look at some periodic trends for these transition elements. As we go across a row, what normally happens to size on the periodic table? It decreases. Remember why?
The nuclear charge.
We have increasing nuclear charge, and the electrons being added are being added to the same principal energy shell. So you've got higher effective nuclear charge, and so it pulls the electrons in. As you go across, the atoms get smaller, which is not what we expect. So here we see a trend in the first 2 that the second one is smaller than the first one. But after that, there's not a lot of change. There's some variability here, but there's not a lot of change. These first electrons are being added in the s block, the s orbital. So whatever n is, ns. And then these are adding in the n-1d. So now we're adding core electrons, and we're adding a proton. And so the effective nuclear charge stays roughly the same as you go across. And so there's not really a good trend. If we go down a group, what do most elements do? So we go down. Size increases. That one makes sense, right? So here, going down, size increases. The rest of these guys, not so much, right? Especially for the, what is that? The third row. The third row's green, yes it is. Yeah, okay, upside down. So as we go down, the periodic table is up on the chart, and the size is increasing. And we do see that from the first row to the second row, but the second row and the third row are all twisted around each other because the f orbitals don't shield very well. And so the fact that those are in there just doesn't make any difference. That's known as the lanthanide contraction, if you're interested. Also known as that if you're not interested. Ionization energy. What do we see as a general trend in the periodic table? You go across a period, ionization energy goes up, increases. Makes sense because the atoms are smaller, right? So the electrons that we're trying to take away are closer to the nucleus, they're held more strongly. We do see this going across. Whoops. So as we're going across, we do see an increase in ionization energy, but it's not as strong as it is for the main group elements. If we're going down a group, let's see if I can get this straight. First ionization energy from the first row to second row to third row actually increases, whereas like for group 1A, as you go down, it decreases, right? So that's opposite. So this is due to the fact that the charge of the nucleus is much higher on those lower elements, but their atomic size is similar, right? So you look at these guys, and the element in the third row has a much higher charge in the nucleus, but the size is very comparable to the other guys. And so a lot of it's the size that affects the ionization energy. Any questions? Electronegativity. Across the row, we see a trend of increasing electronegativity. Is it perfect? No. There are little dips. As we go down a group, we see the opposite trend. We see an increase from the first to the second row, and then no change for the third row. So we see that especially right in here. So going down the periodic table, these are more electronegative, but the second and the third row are the same. The general trend on the whole periodic table, the way I remember it, is fluorine is the most electronegative. And so the closer you are to fluorine, the more electronegative. So going up should get you more electronegative, not going down. Again, the reason for this is small change in size, large change in nuclear charge. Turns out that gold is the most electronegative metal with an electronegativity of 2.4, and compounds of a gold anion have been observed. So, there goes that rule too. Metals always lose electrons, except for gold occasionally.
That's probably why it doesn't tarnish a whole lot.
It's very, very unreactive. Yeah, and you see that too in the electrode potentials. It's just way down there. It's not going to happen. Oxidation states. So, when we learned about oxidation states, we learned group 1A is +1, group 2A is +2, group 3A, meaning aluminum, gallium, and indium, are +3, zinc is 2, and silver is 1, and the rest of them, you look at the name of the formula. Okay? Well, these are the possible oxidation states for this row of transition metals. And if you look at manganese, he can go all the way from +2 up to +7. that's +7, losing 7 electrons. That's, wow, right? And then we've got chromium and iron, and it tails off as we get over to the sides. The +2 is very common. That's this one here. The only one that doesn't make a +2 is scandium. You get the +2 by losing those 4s electrons.